Alright, this video is going to be ugly. I don't know what the rating on it is, but it's certainly not PG. What we're going to do is we're going to look at sine of x squared, and we're going to find y prime. Only here's the twist: find y prime using first principles. So you've noticed the title of this video is why we should use the chain rule. We're going to see exactly why. We don't have anything that lets us take the derivative of sine of x squared using other rules of differentiation. So let's try taking this derivative using limits, and let's see what happens. So this video is really more of an exercise in, I'm not sure if it's sadism or masochism, but possibly both. So y prime is equal to the limit as h goes to 0 of our function evaluated at x plus h. Right, so that would be sine of, instead of x, we put in x plus h. That's the thing that gets squared, minus sine of x squared all over h. And so this is equal to the limit as h goes to 0. First step, the only thing we can do is we can take this x plus h quantity squared and we can expand it. So we can write this as sine of x squared plus 2xh plus h squared minus sine of x squared all over h. Right. Now the only thing that we can do is break this apart. We know what sine of a plus b is equal to. For now, I will take x squared as a and 2xh plus h squared as b, with the full knowledge that I'm probably going to have to expand this afterwards. But at least let's separate the x squared from the rest, because I have an x squared over here. And so there might be some sort of interaction there. So this is the limit as h goes to 0. Sine of a plus b is sine of a times cos of b plus cos of a times sine of b. At this point, it would be easy to forget the minus sine of x squared. Let's make sure we don't do that. All divided by h. Right, so I have sine of x squared here, sine of x squared here. I probably want to factor those out. Keep in mind the x, whether it's here or whether it's here, it's a constant relative to our limit. In our limit, only h is to be considered as a variable. So, what do we have? This is the limit as h goes to 0 of sine of x squared, that's just a constant, times cos of 2xh plus h squared minus 1 all over h. That looks a lot like cos theta minus 1 over theta. So it's something where we expect it to go to 0, but we don't have it immediately. We'll have to play around with it a little bit more. And then plus cos of x squared times sine of 2xh plus h squared all over h. And this looks an awful lot like sine theta over theta. And what's missing? Well, in all of those, let's go with the sine theta over theta. It's the limit as theta goes to 0 of sine theta over theta. That's equal to 1. So this and this and this all have to be the same thing. The one that is solid, the one that we cannot play with, is this right here. Right? I can play around with this h. I can multiply top and bottom by something to change this value. I can play around with the limit goes to 0. As long as I have something which goes to 0, that's perceptible. And this, though, there isn't much that I can do with it. So I have an option. I can either expand it into sine of another a plus b and see what that does, and that certainly works, or I can try to multiply top and bottom by 2xh plus h squared and see what that does. So over here, multiply by 2xh plus h squared divided by itself. Over here, multiply by the same thing. We don't exactly have room for it, so we'll just try to cheat it out. 2x plus h squared over 2xh plus h squared. Absolutely awful, but it kind of works. And so this whole thing goes in a big set of brackets. And we have, first, we can break this up into one limit plus another limit. In each of those limits, sine x squared, cos x squared, these are constants. So we can take them out of the limit. So sine x squared times the limit as h goes to 0 of cos of 2xh plus h squared minus 1 over 2xh plus h squared times 2xh plus h squared over h. All we're doing is switching the order in which we write these guys. Because this right here, the first part of it is cos theta minus 1 over theta. And as h goes to 0, we can definitely say that 2xh plus h squared, which is h times 2x plus h, x is a constant, doesn't matter what the constant is, I'm multiplying it by something that's going to 0, this thing goes to 0. So I can change this into 2xh plus h squared goes to 0, and then plus cosine of x squared times the limit. This time we know what to write right off the bat. Sine of 2xh plus h squared over 2xh plus h squared times 2xh plus h squared over h, everything in brackets, and h's cancel out here and here, and we have sine of x squared times the limit cos theta minus 1 over theta as theta goes to 0 is 1. As this thing goes to 0, or as h goes to 0, this over here goes to just 2x plus cosine, this one over here is 0. That makes more sense. Cosine of x squared times this one is sine theta over theta as theta goes to 0. That's equal to 1 times 2x. And so this is equal to 2x times cosine of x squared. And this is how we find this limit using first principles. And imagine what it would have been like if we had to find sine of x cubed or x to the fourth or anything worse than that. So the chain rule gives us an incredibly powerful way to find limits that would have been nearly impossible beforehand.